Annette, I will present you and then you can go ahead with the presentation. Whoever has any questions, please, as Jan said, place them in the Q&A. It will be easier for me to read them afterwards to Annette. So Annette von der Hart is currently a research associate in the Department of Earth, Ocean and Atmospheric Sciences at the University of British Columbia in Vancouver. She has close to 2 decades of electron microscope experience under her belt and worked with a wide range of makes and models through the years. She received her master's in geology from the University of Bonn and a PhD in geochemistry from the Max Planck Institute for Chemistry in Germany. Her current research interests include developing microanalytical methods with a special focus on trace elements, ultralight elements like boron, carbon, nitrogen, and oxygen analysis, and low voltage application using soft X-ray emission spectroscopy. So Annette, the floor is yours.
Thank you. Okay, I will start by sharing my screen. And I hope everyone can see that. Okay, yes. Excellent. So I will give the first 3 presentations of the day as kind of an intro and primer, specifically for people who are not that familiar with the technique. And just as a caveat, while they're like 40 minutes each, there's, of course, microprobe is a very versatile technique. There are certain aspects. How much you really need to know and understand depends how much, how specific your needs are and so on. So this will give you an introduction, and hopefully for the talks during this week, it will give you the vocabulary to understand when it comes to the more advanced applications. In addition to the talk, I will also share some documents with you, including some recommendation for further reading and kind of like a best practices, just some random thoughts that someone requested last year after the workshop. Okay, good. So let's start. So what is electron microprobe analysis? Often shortened to EPMA or EMPA. I usually see EPMA as the analysis type and EMPA as the tool, but it's not, I wouldn't say it's rigorously defined. And it's one of many microanalytical tools that we have. So various analytical techniques exist for elemental composition, and here are a few. At the lower axis, you can see, let me see. Yeah, this turns it into a laser pointer. You have spatial resolution, and here elemental abundances, and so we usually distinguish between bulk techniques, microanalytical techniques, and now we are getting into the realm also of nanoanalytical techniques. And electron microprobe analysis combines high spatial resolution down to a micron or below with high analytical precision. And one other large advantage is that with a few tips and tricks, we can usually acquire all the way between ppm levels of concentrations all the way up to 100 weight %. And so it's very versatile, and so we can determine compositions on a single spot, whereas a number of other techniques either are not as accurate, or they are not as precise, or they are you have to split analysis a little bit into major, minor, and trace elements, or you can't even reach one or the other. And so this makes microprobe really a very common tool in a lot of material science and earth science departments. Okay, so how does it actually look like? So this is a schematic of an electron microprobe. At its basis, it's like a scanning electron microscope. It has an electron gun. that generates electrons with different types of filaments. And then we have a number of focusing lenses that focus these electrons down on our sample. And then on an SEM, you usually can find electron detectors, specifically secondary electron and backscatter electron detectors, and we find them also on an electron microprobe. And then we have X-ray detectors. On an SEM, you commonly find energy dispersive spectrometers, and on a microprobe, you find in addition also wavelengths dispersive spectrometers. This is really what makes a microprobe, having these wavelengths dispersive spectrometers, and I will talk a little bit more what their components are. In addition, we sometimes find cathodoluminescence detectors and also contamination mitigation or cleaning tools like a plasma cleaner. And another common thing that we find with electron microprobes is that in contrast to certain scanning electron microscopes, we usually do not vent the entire machine. We only vent a small airlock and use it to introduce the sample, as otherwise the pump down time with all these detectors would take too long. And then finally, what is important is that electron microprobes are specifically geared towards stability, because compositional analysis can be many minutes long, and when we do X-ray maps. And so this is something where this platform has high precision stage, a very stable electron gun, and overall, again, has much more electronics and everything than a common scanning electron microscope, and hence they're also much more expensive. There are different types, different manufacturers of EPMA hardware today, although it's getting fewer and fewer. So you can find a JOL microprobes in many laboratories. Chemica, France, was the first one that had a commercial product, and unfortunately ceased production of the regular electron microprobe in 2022. They are only focusing on their shielded electron microprobe for nuclear applications nowadays. And then in addition, we have Shimatsu, but they are not very common in Europe and North America, but you can find them in Japan and China predominantly. All these different manufacturers have slight differences in how they do electron microprobes, have slightly differences in their tools, and so occasionally I will comment on that. But what is important to note as an end user is just that usually they are not like one size fits all analytical recipes or techniques, because they're often specific to the hardware, not of the manufacturer, but also the specific configuration that a lab bought. So understanding certain aspects, what certain hardware components do, what their inherent precision accuracy is, can then be really helpful in trying to translate analytical recipes to whatever you have access to, but also to assess literature data in terms of quality, I want to say, and together with the analytical conditions that are usually stated. Okay, so what makes electron microprobes so useful? I already mentioned, just as with scanning electron microscopes, we have electron imaging. We distinguish between secondary electron imaging, which is using one type of detector. And as you can maybe see here, it is really good to do surface imaging of materials. Usually it has more applications in the material sciences for failure analysis. I will talk in the second talk of today about sample prep, but in general, we like analysis for quantitative analysis, sample preparation for quantitative analysis, having flat polished samples. But if any kind of 3D interpretation is needed, secondary electrons are your tool of choice. And then we have also backscatter electron imaging, a second type of electrons that we generate during analysis. And this is more for first order compositional imaging. And what we have there is, depending on the different gray levels in the image, it's giving us intensities of the backscatter electrons, and they are a representation of the mean atomic number. So when you compare these two images, again, here we can see the 3D topography with like a depression and overall like rough topography. Whereas in the backscatter electron image, you should see here little crystallites in a matrix, and darker color are a sign of dominantly light elements, whereas bright colors are usually directly connected with like high Z elements, high iron or high chromium, or any of these elements. And so we get first order information about the composition, and we can see if a material is overall homogeneous or is zoned, and what the type of zoning looks like if we have multiple phases. And that then in the following helps us to determine where we want to analyze. So in addition, we have these X-ray detectors, EDS and WDS, and specifically the WDS is capable of analyzing elements from beryllium to uranium, in some cases even lithium to uranium, and I think we hear later in the week a little bit about soft X-ray spectrometers. And so we can combine these electron imaging information where we know that overall the mean atomic number of the material changes, in this case here from core to rim, and we can use then the X-rays to actually know what element exactly is changing here. And in this case, iron. And because we can analyze more than one element at a time, we can then turn that even into a phase map and can easily distinguish different types of minerals or inclusions and so on. Okay, so it is very versatile for the chemical characterization of materials, and we have a micron and below spatial resolution for that. The electron microprobe has been very, very important in the discovery of new minerals. Over half of total number of minerals that we know nowadays were discovered since the 1960s. The electron microprobe was, as a concept, introduced in 1949. And so there has been a phase where universities were experimenting with that, and then the first commercial electron microprobe was introduced in 1958 by Kamika. And specifically, it was important in the early characterization of lunar samples and meteorites, because of course, these are type of samples where you don't want to apply bulk techniques, but you need a microanalytical technique. And I should also mention that usually electron microprobe is seen as non-destructive. So in comparison to laser ablation, where we actually like remove material, and same with the SIMS, electron microprobe is not destructive, and so samples can be analyzed again and again and again. So there's a wide-ranging field of applications for electron microprobe. I already mentioned that they're dominantly found in geology and material science departments and laboratories, but usually chemistry, physics, biology, civil engineering, paleontology, soil sciences, archaeology is all many different fields make use of the electron microprobe because of its versatility. And essentially, in terms of samples, we can analyze any material that is solid and that is vacuum stable. So biological materials are not necessarily usually easy to analyze if they contain any kind of moisture, because we run these instruments at a high vacuum, but otherwise everything that is solid and can sustain a beam is possible. And so here are two examples. This is a slag, piece of steel, where people are interested in how homogeneous it is. And here is a nice example from the JOL website, a samurai sword. In looking at cross-sections of an archaeological artifact can tell us a lot about the manufacturing and the type of techniques that were available at previous times. So, and throughout this week, you will hear various applications, probably dominantly in the earth sciences, but again, also other fields that give us where the electron microprobe is very an important part of the analytical workflow. Okay, so again, to understand how this technique works, a little bit on how we generate X-rays. Here on the left-hand side, this is supposed to be a sample consisting of various atoms of different elements. These atoms have a nucleus and electron shells, and usually we distinguish between different electron shells and label them with KLM. So we have a K shell, we have an L shell, we have an M shell that have, depending on the element, different number of electrons. And then here on the right-hand side, this is supposed to be depicting our incident electron beam. So we have electrons bombarding our solid material, the sample. And when that happens, we generate different signals, hence the need for different type of detectors. So up here, this is supposed to be the electron beam. And so if electrons come down on our sample, different things can happen. The first thing is essentially we can miss all the atoms and the electron is just transmitted. The probability that it would never hit anything is relatively small. So when you use transmission electrons microscopy, it's interested in those electrons, and usually you have to thin the sample a lot so that it is so that the electrons can be transmitted. Then when it comes to backscatter electrons, again, we generate different types of electrons in our material. I will not go into Auger electrons. That's usually not something that we analyze on an electron microprobe. It's found on a totally different instrument that's usually standalone. But the backscatter electrons and the secondary electrons are what we're getting. And the backscatter electrons are kind of like near misses of our nucleus that get deflected by the field. And if that happens often enough that they get deflected, they might get back up and can be emitted from the sample surface, hence the backscattering. So there are scattering events, and backscattered electrons are the ones that got deflected, but do not have too many interactions otherwise, so they don't lose energy, their inherent energy that they had from the electron beam. So they're generally high energy electrons, and hence give us some information on the material, because depending how the different elements, it increases or decreases the probability of these events happening. Secondary electrons are electrons that have hit a nucleus and not a nucleus, one of the electrons in the shell, and dislodge one of these electrons, and again through some of these secondary electrons can then be emitted from the sample surface. But the important thing here is that they are usually low energy, and because of that, they can get easily absorbed in the sample itself. And so only the ones closest to the surface get emitted from the sample. Hence why this type of electrons is so sensitive to differences in topography of the sample, and we use them to look at roughness topography, breaking surfaces, and so on. Then what is usually of biggest importance for us are the X-rays. And we generate two types of X-rays in our sample. One are the continuum X-rays that are also called Bremsstrahlung, or often is referred by us just as background. And then the characteristic X-rays. And the characteristics X-rays are so-called because they're characteristic for the element. And those are the ones that we are really interested in to give us the compositions. And they are generated by, again, our beam electron hitting one of the shell electrons. And then we have an additional process. So this is supposed to be a little animation that shows us what happens when we generate X-rays. So up here is our beam electron, here are our shell electrons. And when the beam electron hits our shell electron and dislodges it, nature doesn't like to have unfilled inner shells. And so a higher shell electron takes the position of the dislodged electron. And in that process, X-rays are being emitted, and the energy of that X-ray is the difference between the different shells that were involved in this process. And because the energy levels depend again on the element and the attraction of our nucleus, we get our characteristic X-rays. So each element for a K and L shell ionization process has a more or less unique energy, and that is how we can say what element was generating that X-ray. And here are some examples. So silicon K alpha is would generate X-rays with an energy of 1.74 kilo electron volts. Iron would have 6.45, and so on and so on. You see that the nomenclature that we usually use now tells us always what the donor shell, the emission shell is, so K, and then the alpha tells us what the donor shell was. So in this case, it is one shell over, and so we call it K alpha. Here's another example. Again, our beam electron hits our K shell, but now an M shell, if there's an M shell electron, takes its place, and that gives us a so-called K beta X-ray. And again, this one has a specific energy that is characteristic for this process. So as you can already see, this is the way the naming convention works. And so if we then have that with L shells, so there's also the same probability that instead of the K shell, a beam electron might hit an L shell. And then, so in this case, we call that an L series X-ray. And if it's coming from one shell over, so in this case, the M shell, we call it L alpha. And so which X-rays in particular, we can generate depends on how many shells we have present in an atom. But usually we also generate all these electrons at the same, not these X-rays at the same time. So usually we have multiples. We have a K alpha and a K beta. And if we have more shells, we might have an L alpha, L beta, and so on. Okay. I mentioned that electron microprobe is overall a non-destructive technique, but actually an important thing will also be later in the week when some people talk about glass analysis. It's also important to note already that we're also generating some heat, and that can be a problem. So we're not removing material, but we might alter and damage the material that we're analyzing. Okay. So when it comes to the X-rays that we're generating, we usually get an X-ray spectrum. The X-ray spectrum extends all the way out to what the accelerating voltage is applied at the electron gun. So if we run the instrument at 20 kV, our beam electrons have an energy of 20 kV, and so that is the highest energy that we would find in a spectrum. We call this spot where the intensities go down to the zero, the so-called Handt limit. And it's a quite useful tool to also determine if there's charging as a problem during analysis. Okay, so our X-ray spectrum goes to 20 if we run it at 20. If we run the instrument at 15 kV, it should stop at 15 kV and so on. And then we have overall for the X-ray spectrum this kind of parabolic shape. But because we usually have windows that protect the detector from the vacuum of the instrument that absorb some of the X-rays, usually the actual shape of the X-ray spectrum that we see has this kind of like hump at these low energy side of it. And then, and so this overall shape of the spectrum is coming from the continuum X-rays, or the Bremsstrahlung, and sitting on this are our characteristic X-ray lines. And again, usually if we have K alpha, we might have K beta. And we might have L alpha as well, which would be here at the low energy end. So when we usually want to analyze our element in question, we have the problem that what we really are analyzing are the peak counts or the total counts under the curve, depending on what technique we're using. But the element concentration itself is really determined by the intensity of the characteristic X-ray. But we have the continuum X-rays contribution as well, and the continuum X-rays are being produced by the entire material. So if you think about two materials, an iron oxide and iron sulfide, and let's say an iron carbonate, and they would just, bear with me, happen to have the exact same absolute abundance of iron in these materials, we would get very different peak counts, because while the amount of characteristic X-rays would be the same, more or less, in a very simplified way, the mean atomic number of these materials were different, and our continuum X-rays would differ. So what we usually have to do is we have to find a way to determine what this continuum X-ray contribution is here underneath the peak, and we have to subtract that and get our net counts that are actually then a measure of the total element concentration in our material. And I will talk a little bit more about that in the third talk, also how quantification is handled then with this, but in a early, very simple way. We analyze our X-ray intensities on materials of known composition, often one for each element or just a few simple materials, and then we also we compare these X-ray intensities with the intensities that we're getting from our unknown material. And then in a very, very simple way, which is called Castin's first approximation. Castin essentially is the inventor of the electron microprobe. We can then relate this these intensities relative to the intensities in the standard. We know what the composition of the standard is, and thereby know what the composition of our unknown is if we analyze it for all the different elements. And the advantage of doing it this way is that irrespective how our instrument performs, how good we are at tuning it, we're usually getting accurate concentrations, like the numbers are correct, because whatever we do wrong, or if our machine is just performing a little bit different every day, electron microprobes are very sensitive beasts. It happens both to our unknown material and to our standards. So it essentially factors each other out, and likewise certain X-ray physics are also factoring each other out because they apply to the standard and the unknown. And this is why electron microprobe analysis is so accurate compared to other techniques. In addition, usually we have the problem that while we are analyzing, recording, detecting the emitted X-ray intensities, what we are really interested in are the generated X-ray intensities. And unfortunately, those are not always one-to-one. So if we would just use Castin's first approximation, it would mean that any processes that occur in our sample should have to be the same for our unknown and our standards, which is only true if they have the exact same composition. And of course, when we're analyzing our unknown materials, so even if we would want to do that, we would have the problem that we would have to know what the composition is to know how we would match the standards, defeating the entire purpose of analyzing it. And so again, in the third talk, I will talk a little bit more about this, but in general, we have like three main processes happening during X-ray generation and emission. The first is the mean atomic number that controls essentially how deep our beam electrons penetrate. So this is the Z in corrections. So this is more about the X-ray generation. And then the generated X-rays need to travel through the sample before they can be emitted. And there we have absorption and fluorescence effect. And so usually we have to expand our quantification equation to include terms for the differences in these processes in our standards versus the unknowns. And this is what we usually refer to as matrix corrections. Okay, so when we do electron microprobe, important goals are usually spatial resolution, precision and accuracy and of our data. And what factors into there are certain choices. Some of them you're a little bit locked in, like the choice of EPMA instrument. That's to an extent what you have access to, but still understanding a little bit what the differences between the different instruments can do for you. It can help you see if the lab that you have in your department or that you have easy access to, if that even can do what you are looking for to do. But then within an instrument, there are various choices that we have to do on a day-to-day level, depending on the materials and depending on the question, the application itself, what you're trying to analyze. Are you analyzing trace elements? Are you analyzing major elements? Are you analyzing a specific element as the basis for thermal barometry? And so you need a very high precision for that. Are you analyzing an element for a specific like material property? An example is always steel, where very small differences in carbon can really impact the hardness of the material. And so again, this is something where we have to be relatively precise. And so for our analytical setups, accelerating voltage, beam current, and the beam diameter that we analyze are important variables. Then we have two types of X-ray spectrometers, the WDS and EDS, and they have different pros and cons. And then within the WDS spectrometer, there are choices when it comes to what analyzing crystal and what detector to use that can make a big impact. And then, of course, there are also other choices like how long we analyze something and what kind of standards we want to use. And so I want to talk a little bit about that because this will be a recurring theme then through all the other talks that will talk about these choices. And so, okay. And then in the second talk today, I will talk a little bit about sample preparation. Sometimes it gets forgotten how impactful, important the quality and the choices of sample preparation are. And so that deserves its own talk. Okay, so when you look for electron microprobes, differences start all the way up at the electron gun. And so usually we find three different types of electron guns. The same electron guns you can also find in scanning electron microscopes. And each one has its advantages and disadvantages, hence why they're all three, you can find them in different instruments to purchase. And so we just distinguish between thermionic emission, which is emission aided by temperature, where we heat the filament, versus field emission, where instead the filament is held at a negative potential that's causing field electron emission. But when it comes to electron microprobes, what you usually find are so-called Schottky field emitters, which are a mix between a classic cold field emission and thermally aided emission. So it's a field emission type of cathode that is also being heated. Okay, so how do they differ? The tungsten type filament is probably the most common and still very popular. It gives us the poorest spatial resolution because it's relatively difficult to focus the electrons that we generate at a relatively broad tip all the way down to the sample. And a lot of materials, specifically in the earth sciences, that may not be necessarily a problem because super high resolution is not needed. And when I talk about X-ray analysis, we also have an inherent volume that we actually analyze, which is usually higher than the minimum, size of the beam that we can generate with the tungsten. So it's still very, very popular. And the advantages is that it's relatively cheap to run, both when you buy the instrument, but also the consumables. And in addition, it is a very, very stable beam. And again, we like stability in our beam generation, because the only differences in X-ray intensities that we want to see are supposed to come from the sample and not from our electron beam. Lanthanum hexaborate, cerium hexaborate are just a different material, also part of thermionic emission, and sits kind of in the middle. It's a bit more expensive in running costs and purchase, a little bit less stable, but gives better spatial resolution. And then the best spatial resolution and imaging quality we're getting with field emission, which is a very fine tungsten wire that's etched to a single point and coated with zirconium oxide. So what kind of spatial resolution we can achieve and what kind of imaging quality that we can get starts with our choice of what type of electron microprobe you have access to. And to show you how much that can matter this is an example when I bought a new field emission microprobe and had an older tungsten microprobe. This is the exact same material, a symplectide. And here is the scale bar. So these are 10 microns. And when we compare the tungsten filament with the field emission, you see that overall the spatial resolution is much improved. We get much crisper outlines. The other thing that you see is that there's much less noise, and that is has nothing to do with the field emission versus tungsten, but the fact that modern instruments also have more sensitive crystals, more high intensity crystals, and so you get a much better peak to background. And again, these two maps were acquired at the exact same conditions, same count time, same current, same accelerating voltage. So it really shows what a difference it can make going to a more modern instrument. But if you don't need these sub-micron resolution, tungsten filament machines are just fantastic. And there's a reason that people still buy them. One thing that I want to mention, because it's also important, is that all these different signals that we look at have very different spatial resolution. I already mentioned that secondary electrons usually come from the uppermost few nanometers, and then the backscatter come from a couple of hundred nanometers, and then the continuous X-ray, depending on what we're analyzing and what analytical conditions we use, can come down from a couple of microns. And that's also important because usually we use our electron images to determine where we want to analyze, but we are not getting exactly the same information from these versus what we get from the characteristic X-rays. So that at times it's something useful to keep in mind to do. Okay, so I mentioned that the spatial resolution depends on the material, and here's an example. So with increasing atomic number, we actually generate X-rays in a smaller area. The electrons can penetrate less. These are Monte Carlo simulations of electrons. And again, if there are no electrons, we cannot generate X-rays. So usually we have a better spatial resolution in high Z materials. And then what we can do as an analyst is we can change the accelerating voltage of our analysis. And so with increasing accelerating voltages, we get larger and larger spatial resolution. Now, you might just say that, well, then just always run at the lowest accelerating voltage, but we need a minimum accelerating voltage to generate certain X-rays. Again, their energy is kind of like the minimum energy that you have to put in to get a signal. And so if you want very high resolution analysis, you usually have to combine a field emission machine with low accelerating voltages if it works for your X-ray lines. You might have to use more non-traditional X-ray lines, which can then be a problem in the quantification. But this is really for advanced applications. But yeah, the combination of analytical conditions and your choice of hardware informs what you can do with it. Okay. So I mentioned that you usually need to run a certain accelerating voltage in order to generate your X-rays, and that's where we usually talk about overvoltage. Overvoltage is the ratio of the accelerating voltage relative to the critical excitation energy for a particular X-ray line. So if I want to generate X-ray lines from iron, I need to have more than 6.4 kV as an accelerating voltage to generate a X-ray. And so usually what we find, which gives us the best intensities, is an overvoltage of 2 to 3 times the critical excitation energy. So the intensities that we're seeing here rise with overvoltage. What that number is in absolute kV depends on the X-ray line. And the sweet spot is 2 to 3 times, and then it goes slightly down because absorption increases the further we push our X-ray generation deeper into the sample. Okay, so a few words to our two X-ray detection systems. Again, there's much more to say about details, and there's a lot of good information that I will share, but otherwise you can find on the internet. But just to give you a quick glimpse. So we have the EDS and the WDS on a microprobe, and the EDS you might have already seen are these kind of like simple looking blocks outside, where we have an SDD sensor in the newest generations, silicon lithium drifted detector in the older ones that need additional cooling. And what that does is that we can acquire all X-ray intensities that are being generated at the same time. It's a great technique to get a quick phase ID. Again, we will have peaks at certain parts in the X-ray spectrum that are characteristic of the element, and their absolute abundance is on first approximation representative of the abundance of those elements. And so we can type and get a rough idea of the composition of a material. And so it's especially useful if we have just like an unknown material, and we even need to know what kind of elements we will find. And that's even more important because when it comes to the WDS, usually we have to specify what elements we want to analyze. So if we have no idea what's in the system, we're running into a problem to not know what to analyze for. And it's usually, and obviously we don't want to analyze for the entire periodic table. So how do we do it there? In WDS, detector has two main components, an analyzing crystal and a detector. And this is how it looks like in an actual machine. Here's our analyzing crystal. Down here's our detector. This is a JOL spectrometer where they are both connected with a complicated pulley system because there's a specific geometry that is important during WDS analysis and also in a given spectrometer. So what do we do? WDS uses Bragg's law to filter out the X-ray line of interest. So essentially, instead of analyzing all X-ray lines, we analyze one at a time. We generate
Sorry,
all
Annette.
of them. Yeah, we're
Sorry
running out
to
of time.
interrupt. 6 minutes to break. So if
Okay.
you want for questions,
yeah. I'll try to. I know this is always the one that's a little long. Okay, so we use Bragg's law, n times lambda 2d sinus theta. So we have the wavelengths of the X-ray, the specific placing of the crystal, and then very important, the angle between our sample, the lattice plane and the X-rays, but also the sample and the entire and the crystal. And so again, we use that only the wavelengths of interest gets diffracted out of the crystal. And so we can analyze that at a very high precision because we are also filtering out a lot of the background X-rays. The downside of this technique is that, again, we have to do that, the X-ray detection in kind of a consecutive way. And we usually have to stack elements on the given spectrometers that we have. So we have to analyze one element after another. We can still analyze a lot of elements, but it is a bit more laborious, and it needs to, there are different ways to optimize that. The specific geometry that we have between the sample, the crystal, and the detector is called the Rowland circle. And important here is that the different vendors have different Rowland circles. And so certain positions are really inherent to the type and model of the microprobe that you have for that. However, it is all worth it, because usually when we compare an EDS spectrum with a WDS spectrum on the same material, we find much better spectral resolution, much better peak to background ratios, and much better count rates on the WDS. So while EDS gives us a very quick idea, the WDS gives us oftentimes very precise and accurate data. Usually we have different crystal types in the spectrometer. Each spectrometer can have up to 4, and each crystal type has a specific lattice spacing, and which translates to a specific element range that we can analyze. So there's not one crystal that can analyze the entire periodic table, but instead it brackets a part. And so that's part of the thought when it comes to creating a layout, how we want to analyze something. And nowadays there also, I mentioned, there are high sensitivity crystals. So in more modern instruments, we can find large crystals versus regular crystals, and they are usually having 2 to 3 times the intensities of high sensitivity crystals. And that's important, because then when it comes to count times, like it again depends what specifically you're working with. And this is just an look at a 4 crystal turret that we can flip so that we see 1 crystal. And this is kind of like a graphic representation how the K and the L and the M lines are covered by certain types of crystals.
Sorry, Annette, 3 minutes.
Yeah. Okay, good. Yeah,
for the break.
The detectors are usually, okay, I'm almost at the end, but we can stop here. The detectors are usually something that people have problems understanding anyway, and I would really refer you to the literature. And so there is, it's just another part that needs to be, that the choices get informed. And lastly, with that, we can have a wide range of applications, and you will hear more about that in the following talks. So thank you, and let's then use the time for maybe one question. Perfect. Or you tell me, and I will answer the questions also during the break.
Perfect. Thank you, Annette, for this very comprehensive intro. So there have been 3, 4, 7 questions more. I will read the one that John would like to discuss live. Maybe we can do this later. How often do we have to analyze the standards?
Okay, so that's a good question. And so we have to analyze all standards at least once, because we need to know what kind of intensities we're getting on the day off. And then how often we otherwise analyze them depends really on the stability of your instrument and the stability of your lab. So both temperature variations and at times barometric pressure changes can affect the intensities that we're reading out in the end in the detector. A microprobe is a giant piece of metal, and the crystals are also reacting to have different thermal expansion factors, and specifically the PET crystal is the most temperature sensitive. Likewise, certain X-ray lines have very sharp narrow peaks. And so what happens when we have temperature changes essentially is we wander off the peak. And so when you analyze at the peak, let's say you get 50 counts per second per nanoamp, and when you're off, you get 45. And so you, or even worse. And so if you just relate it to the standard, of course, it needs to be roughly the same. And so if you have very good AC in your lab, if all that is great, I sometimes recalibrate after 2 days. And even that, I don't see drift, but it's still, you don't just want to believe it. You really want to have a good sense what it is. But I also had problems with AC in my lab, and I would just recalibrate every so and so hours. So there is no absolute answer. It really depends on your instrument and your lab. And again, barometric pressure changes can be a problem too. So if you are in California and there's exactly one type of weather, you might have less problems, whereas before I was in the Midwest that has weather with an exclamation mark and all that, and you have like storms running through, and so that can really affect that. But we can specific software can also then handle any drift really well.
Great, thank you, Annette, for answering. And I think we will have the break now, and then when we come back, we can discuss about it, because you will have 2 breaks and before that discussion sessions, Annette. So yeah. I think we can move some questions to be answered then, if that's okay.
Yep.
Perfect. So we will be back here at 3:15.
I was going to mention, Annette, that you know, the standard reanalyzing standards is kind of been a bane through most of my career, because most of the labs I worked in were just, you know, horrible from an environmental stability standpoint, you know. And I mean, until I finally got to Oregon and got to design a lab from scratch in a new building, which is what you got to do in Minnesota, you know, yourself.
Yeah, but they didn't take any of my demands into account, and they ignored it and gave me a normal. But yeah, exactly. I agree, and I've seen it. I heard stories where people calibrate everything at the beginning of the year, and then they just peak because it's so stable. I'm really impressed by that. But I do.
Yeah, go ahead.
Yeah. I see a big difference even with my current lab, where I still don't always trust it, because like so I recalibrate like every 2 days, something like
have you got a temperature monitor in the lab?
Yeah, okay. Of course.
And then how much?
So everyone should have a temperature monitor to know if everything is working, and the temperature monitor should be close to the instrument and not
the
in
instrument
a random
is kind of a temperature monitor.
Yeah.
Right.
But
very expensive temperature monitor.
Yeah, and it needs to be a good temperature monitor, not just some random one. But yeah, it's what I see oftentimes is that I'm glad that I rerun the standard, but there's really no drift. But again, at previous like in Minnesota, I had it that I would see, again, storms would come through. But also in the old lab, the AC was bad. In the new lab, we eventually got it a little bit better, but I think oftentimes universities just don't want to hear that it's important to have an expensive AC, but the effect it has on the quality of data and how often you have to spend time recalibrating really can't be underestimated. Like,
no, I couldn't agree more. But it doesn't have to be expensive. I mean, renovation, of course, is always problematic because, if you're not designing from scratch, then you've got to work with what you have, and that can get down a rabbit hole. But I will say that the lab that we designed in Oregon, the Camcor lab that you've been to, those are just standard Siemens reheat units, and they just been basically, we had a very talented engineer, HVAC engineer, and he basically reprogrammed them from their default factory settings, because normally these units are intended just for office buildings, and it's not that critical. So, but he modified the firmware in them so that they would really keep the temperature very, very stable. And we're easily within 0.2 degrees C plus or minus on a 24-hour basis. I was just in there yesterday and I just happened to glance over at the temperature monitor and it was a flat line, and so, it can be done and it doesn't have to be expensive, but it has to be, like you said, people willing to listen to us and feel that it's worth the effort. And the only way I was able to accomplish that, I think, in this case, was just that I kind of challenged the engineer and said, I bet you can't do this. And he was, I think I can. I said, no, you can't. You won't be able to do it. So he took it as a kind of a personal challenge to try to prove me wrong. And I was very glad that he was able to prove me wrong. So that worked out well.
Yeah.
Annette, I see that you're already doing it, which is great.
I'm answering questions at the same time.
Feel free, you're multitasking.
Yeah.
Feel free to answer whatever has been already answered as well, if you wish. And though I see here John has tackled.
What's that?
Most. I see here that you have already tackled most.
Well, I was just trying to answer some that I thought were just textbook questions. But I will just add to the discussion about reanalyzing standards, is that it got to the point early on when I was in some of the labs I was in early in my career that I was forced to add what I call the standard intensity drift correction to our software. And so it means that every time you restandardize, that intensity is recorded and is timestamped. And so when you analyze unknown materials in between the standardizations, it uses the standard intensity that's interpolated between the standardizations. So if you got, 10,000 counts per second on a standard, on an element in the standard at noon, and then 4 hours later you restandardize and you got 12,000 counts per second, then when you do the analysis of any unknowns in between there, it would do a drift correction and calculate what the standard intensity, assuming a linear drift correction, of course, because that's all you can do. But it would interpolate the standard intensity, and then you use that for any unknown analyses, and that worked amazingly well. And I would have people, sometimes in the morning come to me and say, "Oh, I ran overnight, and all the analyses look pretty good, but as morning came around, the totals are now up to 101 or 102%. What can I do?" And I said, "Oh, just restandardize." And they'd restandardize, and also they go, "Oh, now everything's fine. Thank you so much." So the drift correction can be important if the lab is really suffering from stability problems in terms of temperature. And Annette mentioned the PET crystals being probably the most problematic of the Bragg crystals because it has the largest coefficient of thermal expansion. So it's the most affected by that.
Why are the detection limits the same? Dismissed. That seems like a misclick.
Because he also underneath that said that his question was just answered. But if you wish to say anything more about the configuration.
What was the question that was dismissed?
If the detection limits of EDS and WDS are the same.
Oh. Yeah, I mean,
actually, I have reopened the question, so it's already now listed in the questions. It's reopened.
If you want to type there.
Yeah, if you want to
now
type something, it's there.
yeah, while Annette's typing, I can just chime in and it's basically an issue of the fact that the EDS is a wonderful technique because it sees the entire spectrum. The problem with EDS is that it sees the entire spectrum. If you catch the joke, you know, seeing everything all at once is wonderful, but it does have some downsides. And one of the downsides is that if you think about this, let's say you're interested in a particular emission line, you know, say silicon or titanium or whatever. So when you're looking at that titanium emission line, every other photon that comes into the detector is not contributing to your signal, but it is contributing to the dead time of the system. And so what you'd really like to do is have a type of instrument where it only looked at the titanium emission lines, or at least the X-rays in that region. And that's what WDS does. So that's what the word dispersive means, is so that WDS is basically dispersing away from the detector all the X-rays that are not currently of interest. And that contributes to the downside of WDS, which Annette pointed out, which is that you have to analyze a lot of these elements in series. I mean, you can measure them in parallel depending on how many spectrometers you have, but then when you have more than, you know, say 4 or 5 elements, then you have to analyze them in series. But you do get a benefit because you're very focused on just those emission X-rays, and the tiny amount of continuum is underneath them. And of course, detection limit is determined by the peak to background ratio. So if you have a lot of peak intensity and very low background intensity, you have very good sensitivity. And that's the main difference between EDS and WDS in terms of sensitivity. Okay, so someone's asking me if I want to quantify only TiO2 for my sample, do I need to use the WDS system? And the answer is no, you don't have to use the WDS system. It's just that in fact, the WDS system can analyze major elements, but also trace elements, and the EDS has more difficulty with trace elements. So I would say it depends what you're trying to analyze in TiO2. If you're trying to analyze the ratio of titanium to oxygen, then EDS would work. Well, okay, there's an interference there, so that's going to be problematic. But if you're looking at, you know, the ratio of iron to titanium, say in an iron titanium oxide, you could use EDS. But if you're trying to measure trace elements in TiO2, then you might be better off using WDS. And if you're trying to measure the oxygen ratio to titanium versus titanium monoxide, then you probably would want to use WDS, just because the oxygen light elements can be problematic in EDS, just because the lower spectral resolution and the higher incidence of interferences. And someone says, should I recalibrate every time the tungsten filament is changed? And the answer is, oh no, you only need to calibrate once every 20 years. I'm joking, of course. Yes. But the answer is actually more subtle than that, is that you wouldn't necessarily have to recalibrate if you change the tungsten filament, because you're measuring the beam current with a Faraday cup, so it should be normalized. However, you have now vented the gun and repumped it down, so as long as nothing else on the instrument changed, you might be okay, but the only way to know is to re-standardize, and then you'll see if it was necessary or not. So you only know after the fact, is the way I would put it.
What I do in general with restandardization, again, there are certain X-ray lines, not so much elements, that are kind of the canary in the coal mine. So it's not that if I restandardize, I necessarily restandardize all elements on the various spectrometers, but I specifically if I'm like manually, like if I do it interactively, I usually restandardize the silicon. Because that's a fairly sharp peak, and it's probably in earth science applications the most important one, makes up 50% of the element abundance. And then I might also check an element on the PET, like calcium or something. And if those don't drift, the likelihood that any of the other ones drift is much lower. So if you want to cut time, that's definitely a good approach to kind of like see and start with the usual suspects first. And I would also make like the LAF X-ray lines on the LAF doesn't drift so much, and usually they're also more in the trace element range. So if I have like a 2% drift, doesn't matter at a element that has like 0.1 weight percent, my precision is much worse. I mean, usually we want to be analyze as good as possible, but again, there are like certain ones that I would start with and then take it from there to see how much my system
Perfect. Thank you, Annette.
changes.